Hello everyone, today I will be presenting a little home experiment that I did comparing the observed contact angle to the spherical approximation of contact angle on a stainless steel surface, and then use these measurements to determine some of the stainless steel surface properties. To perform this experiment, I needed a few materials. I used stainless steel as my surface to place the droplets onto. I used water as my liquid, which was dyed with some blue food coloring. I used a pipette to grow the droplets and place them onto the surface, and then a pair of calipers to be able to measure the droplets and collect data for the experiment. So to go over some of the theory behind this method, we can use the spherical approximation of a droplet on a surface to be able to determine the contact angle theta, given the height and the radius of the droplet, as well as the distance from the outer edge of the droplet to the center of the droplet. And then, assuming that that angle that we are able to actually determine is theta, we can then use the Young-Dupert equation to determine spreading, and as well as the work of cohesion/adhesion on that surface. The procedure for this experiment is relatively simple. I'll use a pipette to grow the water droplet and carefully place it onto the surface. Then I will use the calipers to measure the height and diameter of the droplet, as well as take a photo to analyze the observed contact angle later. Now, from the experiment, I did this 10 times and collected the diameter, height, and was able to determine the spherical estimation, as well as go through the data using the image processing software to determine the contact angles. So for the overall experiment of the averages, I was able to get an estimated contact angle of 65.6 degrees using the spherical approximation, and then from the observed contact angle, I measured both the left and the right sides of a spherical droplet and then determined an average. Now, ironically, it turned out that the left and right side averages ended up being exactly the same over the course of the 10 droplets. So for that one, I got an observed angle of 70.5 degrees. So that shows about an 8% variation overall throughout the experiment. To get a better understanding of the estimations of theta from the two different methods, I plotted them, and as you can see, the spherical estimation in orange typically is lower than the observed angle that we were able to measure using the software solution. Now, this could be due to some variations that I'll talk about later, but it was interesting to see that trend in the data. So using the data, we are then able to go and determine some of the surface properties for the stainless steel sheet that I was using. So to determine spreading, based on the spherical approximation and the observed approximation, both ended up showing a negative value for the spreading factor, which does show that, as expected, the surface is not spreading and is actually getting partially wetted by the water droplet on the surface, which is expected given the properties of stainless steel. And then we were able to further go and determine the work of cohesion/adhesion, which for this was about based using the sphere method to determine contact angle was 101.45 millinewtons per meter, and then the observed was 96.03 millinewtons per meter. Shown here on this slide is the 10 droplets analyzed in this experiment. Generally speaking, they were pretty uniform. However, there were some variations in each of the droplets, such as differences in the left and right side contact angles, them not being perfectly circular on the surface, and other variations like that could cause some error in the experiment. In addition, I couldn't validate that the size of the droplets was exactly the same in each droplet, and that would cause a variation in the height and measured diameter, which would lead to further error, as well as it is possible that these droplets might be a little bit too large to be able to consider the spherical estimate as a method of determining contact angle. Using previous experimental data that I used in the last experiment, I was able to determine that Each drop was about 0.02 milliliters, that's about 20 microliters. And even at that size, it still may be too large to be able to use this method due to the effects of gravity. Some of the general conclusions from the experiment is that I was able to determine the contact angle using the spherical method to have about an 8% variation between it and the observed contact angle. And typically this was an underestimation when compared with the observed contact angle, and there were a couple different potential sources of error, such as the drop size being too large, and possibly having an effect, gravity having an effect on the droplet, possible non-uniform volume in each droplet causing variations in small variations in radius and height measured, as well as possibly some non-uniform surface features of the stainless steel sheet that I was using. The sheet was prepped in advance, however, throughout the course of the experiment, there could have been some imperfections to the surface that caused the droplets to behave differently. And then some possible effects from placing the droplets, and then general human error in reading the diameter and the height with the calipers. Well, that was my experiment. Thank you very much.